When people talk about the future of artificial intelligence, the conversation almost always begins with faster chips. The spotlight falls on powerful GPUs, cutting-edge semiconductor factories, and the race to build ever larger AI models. The assumption seems obvious. Whoever produces the most advanced processors will lead the next generation of computing. But what if that isn't the entire story? Imagine a data center filled with tens of thousands of the world's fastest AI accelerators. Each processor is capable of performing extraordinary calculations every second. Yet, if those processors cannot exchange information quickly enough, much of that computing power sits idle, waiting instead of working. In modern AI systems, speed is determined not only by how fast each chip thinks, but by how efficiently every chip communicates with the rest. That brings attention to a technology that rarely appears in headlines: optical fiber. These ultra-thin strands of engineered glass quietly carry enormous volumes of data between servers, networking equipment, and entire data center campuses. As AI clusters continue growing in size, this communication network is becoming just as essential as the processors themselves. So the real question may no longer be whether the industry can build faster GPUs. It may be whether it can build the infrastructure capable of connecting them into one coordinated machine. The next major challenge in artificial intelligence could be hidden not inside the chip, but in the network that allows every chip to work together. Training today's most advanced AI models is no longer the job of a single processor. Instead, the workload is divided across thousands of GPUs operating simultaneously, with each chip responsible for only a small portion of the overall calculation. This approach allows AI systems to solve problems at a scale that would be impossible for any individual processor. However, it also creates a new challenge that becomes more significant as clusters continue to grow. Every GPU must constantly exchange information with thousands of others. After completing one stage of computation, each processor sends updated data across the network before the next stage can begin. This cycle repeats millions of times during the training of a large language model or other advanced AI system. If even a small portion of the network falls behind, the entire cluster is forced to wait. A useful way to think about it is as a team of experts working on a massive engineering project. Every member may complete their own assignment quickly, but progress slows dramatically if drawings, measurements, and design changes cannot move efficiently between departments. The bottleneck is no longer the workers. It is the communication system connecting them. Modern AI data centers operate under the same principle. The processors perform extraordinary amounts of computation, but they are equally dependent on the network that allows them to coordinate every task. As clusters expand from thousands to tens of thousands of accelerators, communication becomes an increasingly larger share of the overall workload. This shift is changing how companies design AI infrastructure. Performance is no longer measured solely by the capability of individual chips. Instead, engineers must consider the entire system, including networking equipment, switching architecture, and the physical connections carrying data between machines. A powerful processor delivers its full value only when information can reach it without delay. In many ways, AI has transformed networking from a supporting technology into a core component of computing itself. The faster processors become, the more critical, efficient communication becomes alongside them. Traditional data centers were designed around a relatively straightforward pattern of communication. A user sends a request, a server processes it, and the response is delivered back. Most of the data moves into the facility and then back out again. While this requires substantial networking capacity, the traffic generally follows predictable paths. AI data centers operate very differently. Instead of communicating primarily with outside users, the vast majority of data moves internally. Thousands of GPUs exchange information with one another continuously, sending model updates between servers, racks, switches, and even separate buildings within the same computing campus. This constant machine-to-machine communication has become one of the defining characteristics of modern AI infrastructure. As AI clusters grow larger, the number of possible connections grows even faster. Adding more processors does not simply increase computing power, it also increases the volume of data that must travel across the network. Every additional GPU creates new communication paths that must remain fast, reliable, and synchronized with the rest of the system. This is why AI facilities require dramatically more networking hardware than conventional cloud environments. More processors lead to more network ports. More ports require additional switches, optical transceivers, connectors, and ultimately, far more optical fiber. The relationship is not always proportional. In many cases, networking complexity expands faster than the number of processors themselves. The result is a fundamental change in infrastructure planning. Building an advanced AI data center is no longer just about purchasing the latest GPUs. Companies must also secure the networking equipment capable of keeping those processors working together without interruption. Increasingly, the performance of the entire system depends on the strength of the connections between the chips, not simply the chips themselves. This growing demand explains why optical networking has moved from being a background technology to one of the fastest growing segments of the AI supply chain. As investment in artificial intelligence accelerates worldwide, the need for high-capacity fiber infrastructure is expanding alongside it, turning what was once considered ordinary networking equipment into a strategic component of the industry's future. For decades, copper cables form the foundation of data communication inside servers and networking equipment. They remain reliable, relatively inexpensive, and highly effective over short distances. Even today, copper continues to play an important role in connecting components within individual machines and nearby hardware. However, artificial intelligence is pushing data transmission to levels that traditional electrical connections were never designed to support. As network speeds move from hundreds of gigabits per second toward even higher capacities, electrical signals traveling through copper encounter increasing challenges. Signal quality becomes more difficult to maintain, power consumption rises, and heat generation becomes a growing concern. The farther those signals travel, the more engineering is required to preserve speed and reliability. Optical fiber addresses many of these limitations by replacing electrical signals with pulses of light. Instead of moving electrons through metal conductors, information travels through an ultra-pure glass core with remarkably low signal loss. This allows enormous amounts of data to move across much greater distances while consuming less power and generating less heat than comparable electrical links. These advantages are becoming increasingly important inside modern AI data centers. Massive GPU clusters often span multiple rows of racks, separate rooms, and sometimes entire buildings. Maintaining high-speed communication across these environments requires a technology capable of delivering both bandwidth and consistency. Optical fiber has become the preferred solution because it scales far more effectively as networks continue expanding. The transition is also changing the design of networking hardware itself. In earlier generations, optical components were typically positioned at the edge of network switches, where incoming light signals were converted into electrical data before reaching the switching chip. While this architecture proved successful for many years, it introduces additional power consumption and heat as bandwidth requirements continue rising. To improve efficiency, manufacturers are increasingly developing systems that move optical technology closer to the networking silicon. By shortening the electrical pathways inside the equipment, more of the data's journey remains in the optical domain, reducing energy loss while supporting much larger AI clusters. This architectural shift is expected to become increasingly important as future networks operate at even higher transmission speeds. Ironically, bringing light closer to the processor does not reduce the need for optical fiber. It strengthens it. Every improvement in optical networking creates demand for additional fiber connections, advanced connectors, precision optical components, and increasingly sophisticated manufacturing capabilities. In other words, the evolution of AI networking is not replacing glass with something new. It is making glass an even more central part of the computing infrastructure. As processors become faster and AI systems grow larger, optical connectivity is evolving from a supporting technology into one of the essential foundations of next-generation computing. As demand for AI infrastructure continues to accelerate, the challenge is no longer limited to designing faster processors. An equally important question is whether the global supply chain can produce enough networking components to keep pace. For optical fiber manufacturers, this has become one of the fastest changing markets in decades. Industry reports indicate that many major producers are operating at extremely high utilization levels, with delivery schedules for certain specialized optical products extending well into future production cycles. This does not mean the world has run out of fiber. Rather, it reflects a market where a growing share of manufacturing capacity has already been reserved by customers planning large AI deployments. The distinction is important. Standard telecommunications fiber remains widely available for many traditional applications. The greatest pressure is concentrated in specialized products designed for advanced data centers, where thousands of high-speed connections must fit into limited physical space while maintaining exceptional signal quality. These requirements demand fibers with tighter manufacturing tolerances, improved durability, and lower transmission losses than conventional networking installations. As AI companies continue building larger computing clusters, orders are arriving faster than factories can expand their output. New customers may still secure supply, but delivery times have become noticeably longer as manufacturers work through existing commitments. The speed of this demand increase has surprised much of the industry. For years, optical fiber production was driven primarily by broadband expansion, mobile communications, and telecommunications infrastructure. AI has introduced a completely different growth engine. Instead of extending networks to millions of households and businesses, manufacturers are now supplying enormous computing facilities where every additional rack may require hundreds or even thousands of new optical connections. This shift has changed how technology companies approach procurement. Rather than purchasing networking equipment only when new facilities are ready for installation, many organizations are securing production capacity years in advance. Long-term supply agreements, strategic investments, and manufacturing partnerships have become increasingly common as companies seek greater certainty over future deliveries. The reason is straightforward. Expanding production cannot happen overnight. Building additional manufacturing capacity requires substantial capital investment, specialized equipment, highly trained personnel, and extensive quality control systems. Even after construction begins, bringing a new production line to commercial scale can take many months, or in some cases, several years. That creates a timing mismatch between supply and demand. AI investment cycles can accelerate rapidly as new technologies emerge and computing requirements increase. Manufacturing expansion, however, follows a much slower timetable. Factories cannot simply double output because demand has doubled. As a result, the discussion surrounding AI infrastructure is beginning to evolve. Instead of focusing exclusively on semiconductor production, investors and industry leaders are paying greater attention to the broader supply chain that supports large-scale computing. Optical fiber has become part of that conversation, not because it is rare, but because producing the highest performance products at sufficient scale requires time, expertise, and long-term planning. In many respects, this reflects a familiar pattern seen throughout technology history. Breakthrough innovations often create unexpected pressure on industries that previously attracted little public attention. Today, optical fiber manufacturing is emerging as one of those critical links, quietly determining how quickly the next generation of AI infrastructure can be built. At first glance, optical fiber appears remarkably simple. It is thin, lightweight, and made primarily from glass. Compared with the sophisticated processors powering AI systems, it may seem like an ordinary industrial product. In reality, manufacturing high-performance optical fiber is one of the most precise processes in modern materials engineering. Everything begins with a component known as a preform. Rather than a long strand of fiber, a preform is a large cylinder of ultra-pure glass that contains the exact internal structure the finished fiber will eventually have. Engineers carefully control the chemical composition of every layer, ensuring that light will travel efficiently through the final product with minimal signal loss. Even microscopic imperfections can reduce performance. Tiny contaminants, slight variations in material density, or small inconsistencies in the manufacturing process may weaken signal quality over long distances. For AI networking, where enormous volumes of information move continuously between thousands of processors, those details matter. Once the preform has been completed, it enters a specialized drawing tower. The lower end of the glass cylinder is heated until it softens, allowing a continuous strand of fiber to be pulled downward under carefully controlled conditions. Throughout this process, the diameter of the fiber must remain almost perfectly uniform. Sophisticated monitoring systems constantly measure the strand, making real-time adjustments to maintain strict production standards. Immediately after the fiber is formed, protective coatings are applied to shield the glass from damage. The material then undergoes extensive testing before being bundled into cables that will eventually serve telecommunications networks, cloud computing facilities, and increasingly advanced AI data centers. While this process sounds straightforward in principle, expanding production is considerably more difficult. Building new manufacturing capacity requires highly specialized equipment, clean production environments, advanced chemical processing systems, and engineers with years of technical experience. Every stage must meet exceptionally high quality standards, because the finished product is expected to carry data over long distances with extraordinary reliability. The greatest challenge often lies at the very beginning of the supply chain. Producing additional preforms is significantly more complex than assembling finished cables. New facilities require substantial investment, specialized manufacturing technology, and lengthy construction timelines before they become fully operational. As a result, increasing output cannot happen quickly simply because market demand rises. This explains why the optical fiber industry responds differently from many other manufacturing sectors. AI infrastructure investment can accelerate within months as companies announce new data center projects. Expanding glass production, however, often requires years of planning, financing, equipment installation, and operational testing before meaningful additional capacity reaches the market. For investors and technology companies alike, this creates an important reality. The true bottleneck is not necessarily the final cable that arrives at a data center. It is the sophisticated manufacturing process that transforms highly engineered glass into the ultra-fast communication network modern artificial intelligence depends upon. In the race to expand AI infrastructure, producing more optical fiber is not simply a matter of making more glass. It is a challenge of precision engineering, advanced material science, and long-term industrial investment, factors that are becoming just as important as the processors those fibers are built to connect. The rapid rise of artificial intelligence is doing more than increasing demand for computing power. It is reshaping global manufacturing priorities and forcing companies to reconsider where critical infrastructure is produced. Optical fiber has become one of the clearest examples of this transformation. For many years, the optical fiber industry experienced periods of intense competition. Massive investments made during the global expansion of broadband networks and mobile communications created substantial production capacity. In some regions, manufacturers struggled with oversupply, narrowing profit margins, and cautious investment decisions as demand stabilized. The AI boom has changed that equation. Facilities originally built to support telecommunications are now becoming essential to the construction of advanced AI data centers. Instead of connecting homes and businesses, increasing volumes of optical fiber are being directed toward massive computing campuses where thousands of GPUs must communicate continuously at extremely high speeds. This shift has placed countries with well-established manufacturing ecosystems in a strong position. China, in particular, has developed one of the world's largest optical fiber industries through decades of investment in telecommunications, infrastructure, advanced materials production, and large-scale manufacturing. Today, that existing industrial base is supplying both domestic AI projects and an expanding number of international customers. However, the response is not limited to one region. Technology companies are increasingly seeking to diversify their supply chains while strengthening domestic production capabilities. Rather than relying entirely on traditional purchasing agreements, several major firms have announced long-term partnerships and investments aimed at expanding optical networking capacity closer to their own operations. These agreements represent more than routine supplier relationships. By committing capital to manufacturers and securing production years in advance, technology companies are attempting to reduce uncertainty in one of the fastest-growing segments of AI infrastructure. The objective is not simply to purchase fiber when it is needed, but to ensure that future manufacturing capacity already exists before demand reaches its peak. This strategy reflects a broader change in corporate planning. Components once viewed as interchangeable commodities are increasingly being treated as strategic assets. Companies now recognize that reliable access to networking infrastructure can be just as important as access to advanced processors. The impact extends throughout the supply chain. Manufacturers are investing in new facilities, expanding production lines, and increasing research into higher performance optical products designed specifically for AI applications. At the same time, governments and industry leaders are paying closer attention to the resilience of critical manufacturing sectors that support next-generation computing. Ultimately, the AI revolution is influencing far more than semiconductor production. It is reshaping the entire ecosystem behind digital infrastructure, from advanced materials and precision manufacturing to long-term supply agreements and industrial investment strategies. Optical fiber, once considered a quiet part of the technology industry, has become a strategic resource whose importance continues to grow alongside artificial intelligence itself.